All right. Hey guys. This is just a lesson sort of on the structure of how we're gonna go about doing this, um, going about how we're going to make this robot and sort of how I'm going to assign things to you. So right here we've just got a pretty basic sketch. And I'm gonna be giving this to you guys. I'm gonna be giving probably one or two or three sketches to you, and I'm gonna expect you guys to make a full assembly from that. Um, so I'm gonna go about what you should expect from this, and once I finish explaining things, then you guys are gonna stop. You're gonna pause, and you're going to make your own model, and then once you make your model, your assembly, you're gonna continue then on the rest of the video, and you're gonna see where it's different, where you might have missed something, where you did something you didn't need to do, and then it'll just be a way to sort of reflect on what you can improve on. So right here is our sketch, and I have another sketch, and I'll just go with talking about what everything is. So right here and right here, these two circles are representing Falcon motors. And this right here is representing a 48 tooth 20 DP gear, which all that I'll get into in a second. And these two circles right here represents two Falcon pinion gears, each 12 teeth each. And then this hexagon right here, that represents our hex shaft. That's our output shaft. And so this whole thing is meant to be a transmission. It obviously doesn't look like that. It's just a bunch of circles and a rectangle, a bunch of circles and a hexagon. But whenever I show you this sketch, then it might make a little bit more sense. So these two rectangles again are the Falcons, and then these two right here and right here, these two rectangles are the 12 tooth pinion gears, and then this rectangle right here is the 48 tooth gear. But then we have our half-inch hex shaft right here. But then there's a couple new things. So right here is a 1/4-inch thick plate. These two rectangles are 1/4-inch thick plate. And then there's this rectangle right here and this rectangle right here. And those are meant to represent the bearing flanges, where they stick out in the whole assembly. So whenever I give you a task, I'll give you a couple sketches. We might be in a Zoom, or I'll give you a recording like this, and I'll say, this is a Falcon, this is that, and then I'll expect you to just make it. So let's go over what all the heck I just talked about. So Falcon motors. Falcon 500 VEX here. So this is a Falcon 500. This is the motor that we are going to be using for this. You guys are probably familiar with this unless you're new. If you're new, these are just a motor that we use. And then we can see this is the whole pattern, which is going to be very important for you. This is the usable shaft length, which is not as important for you, but it will be important for later things. And then the overall length I didn't bother putting in the sketches because that doesn't really matter. Then bearings, these are what bearings are. This hexagon shape is specifically for this kind of bearing that we're using, and bearings can either have a flange or have no flange. We're going to be having bearings with a flange, and that's so that they can stay on the, they don't move around. These are the pinion gears I was talking about. You have to have pinion gears anytime you want a motor to have any kind of gearing to it outside of the motor. What's a better way to say that? Pinion is basically means it's attached to the motor shaft. So Falcons, they have this weird shaft that's like it's got a bunch of lines going down it, and we call it a spline gear shaft. Basically a fancy way of saying it's really annoying. Wait, there we go. So that's the whole pattern that it has. And then it's a 12-tooth pinion gear. So it has all these different things associated with it. And then when I mean 20 DP gear, this is what I'm talking about. 20 DP has to, it's like the relationship between the diameter and how many teeth there are. It's just basically how many inches, how many teeth per inch of circumference there are. Actually, it has to do with how many teeth there are per inch of diameter. So if there is a 10-tooth gear at 20 dp, then its pitch diameter is going to be ½ an inch, if that makes sense. I don't know if it does, but we'll move on. So it's just a type of gear, and only 20 dp gears will interlock with 20 other 20 dp gears. If I have a 20 dp and a 21 dp, they're not going to work together. It just does not work whatsoever. And so this is what they look like, and over here we have 48 teeth in this table here. And if you're wondering why I'm going to all these different websites, you're going to have to be pulling the CAD from these websites. Or if I set it up in time, we'll have like a universal GradCAD library to get things from. But if not, you're going to be going to these websites and scrolling down all the way, going to CAD files, downloading the CAD file for all these different things, and then going into your assembly and then putting them in. So yeah, I think that covers it just about. This is just transmission. You have your materials. I will not go as in depth with like the websites whenever I'm giving this to you. I'll probably just be like, here, this is a Falcon. This is a 12-tooth pinion gear. This is a 48-tooth 20 dp gear. This is a plate. This is a plate. This is a shaft. These are meant to represent bearings. That's all I'll give you, and then you just run with it. So, if you followed so far, great. Stop here and make your own assembly. Make the whole thing. And then once you make it, you can come back, and then we will go over how to go about it the way I intend you to go about it. So pause, make your thing, come back. All right, welcome back. Now we have to make our assembly. So let's make a list of everything that we're gonna need. We are gonna need 2 Falcon 500s. 2 Falcon 500s. We're going to need 2 Falcon 500 spline pinion gears. And they're 12 teeth. And we're going to need 1 48-tooth 20 dp gear. And we're going to need 2 flanged ½ inch hex bearings. We're we're going to need this 48 tooth 20 DP gear to be 1/2 inch hex bore. And then, let's see, falcons, gears, gear, bearings, and then we'll have and we need 1/2 inch hex shaft. Okay, cool. So these are all the parts that we're gonna need to make this. I'll give you guys these sketches, by the way. It sucks for you guys because you'll have to, actually I'll probably end up sending these sketches to you and the video. So you'll have these sketches anyway. So what you need to start off doing is, I always like to work in sketches before I do anything. And then I'll often use like the whole sketch in my assembly. Actually, I should probably not do that because I don't think that would be very good. So I'm gonna make a new sketch. So I have to define that I'm using that, and then make a new sketch. And then I have, let's see, I have my 2 Falcon motors, 2.362. These are equal. I put these apart from each other, center line, tie them together. Then these 2 lines are equal, and they are horizontal. Cool. And this is, yeah, these 2 are equal. Okay, cool. So these are my 2 Falcon motors. And I need them to be measure this and measure this, 1.5 inches from the center. So 1.5. All right, and then these are actually not needed. And so then, sorry, before I get into anything, let me explain what I'm doing. So I just sort of made a brief reconstruction of this. And so now, so I'm going to be making the plates. I should probably start off by saying that I'm going to be making the plates first. The mounting plates, of which we're going to put everything on, sandwich everything in between. So what my first thing I'm going to do is I'm going to look at the Falcon 500, and I'm going to look at the mounting holes. So there's 6 of them, and they are all on a circle that is 2 inches in diameter. So if I go back to my sketch, I can take a circle, then draw a line there to there. This is, yep, horizontal. And then this, I believe, hold on, let me check. I believe it's 1032 tapped hole. So I know it off the top of my head. A 1032 is 0.201. We should probably make a standard thing for that, but whatever. Because sometimes people put 201, 0.2, 0.195. It can get a little confusing. So we're going to have this be 1 inch, because 1 inch is the radius, if 2 inches is the diameter. And then what we're going to do is we're going to select that go up to circular sketch pattern, and instead of selecting that, we're going to select this right here. No, delete that, and instead make it that center of the circle right there. And then it wants me to make 4, but I'm going to change that, and I'm going to have it make 6. So I'm going to have it dimension the radius like that. Actually, I don't need it to do that. I should not have had it dimension the radius. I'm sorry. Oh my gosh, what did I do? I'm just going to go back to before I dimensioned the radius. Go back, go back. All right. Go back to circular sketch pattern. No, I don't want it to be right there. I want it to be right there. And then I'm going to make it 6. I'm not going to dimension the radius because I don't want it to do that. And then I'm going to select that. And then we've got our whole pattern. And then if I want to copy that over to the other side, I'm going to make a line from the origin just going straight down. It's going to be vertical, and we're going to call it infinite lengths just so that we know exactly what its purpose is. But before we mirror it, which is what we're going to be doing, we also need to make the middle hole. So we're going to go back to the falcon, and the shaft. It doesn't tell me what size the shaft is. What size is the shaft? It doesn't tell me. Okay, I'm just going to go to the okay, it doesn't tell me what the shaft diameter is. But basically what we want to do is we want to size the hole in the plate to be too small for the gear to fit, but big enough for the shaft to fit. So this gear is 0.7 in outer diameter, 0.6 in pitch diameter. So we're going to say 0.5 will be the hole. Will be this hole right here. So let's call that 0.5, and then we've got all that out, and yep, that looks good to me. And then we're going to take all of this. We can actually delete that, and we can delete that, and we can take this whole thing, and then we can mirror over this. Yep. And then we get the exact copy just right over there. And so now I've got this, but then there's one last thing I need to do. I need to make a thing for my bearing, which is going to be 1.125. But oh no, Dan, there's a problem. If this is, oh wait, I didn't explain. The size of the bearing is 1.125 on the inside. The flange is either a 16th or a little bit more than a 16th. Maybe it's an 1/8 extra on the outside. I think it's an 1/8 larger for diameter. But anyway, oh no, Dan, it's in the way of this hole pattern. What are we gonna do? Well, we can do two things. We could move this whole hole pattern to where it's rotated so that like this gap between these two holes perfectly fits with this bearing hole, and then it is all perfectly aligned and everything works. Or we could just take these two, put them for construction, and then we're done. Because the motor doesn't need to mount to all 6 bolt things. In fact, it's a waste of weight if you do that, because you really only need 3 mounting bolts per motor. 4 is cool, 5 is cool, 6 is cool, but beyond 3 or 4, you're kind of wasting weight because you're gonna have just about the same amount of fastening. So that's our bearing hole. These are all our mounting holes. And then all we need to do now is we just need to make the plate. So we can do this really, really, really fast by making a slot. So boom, that's all I had to do. Made a slot, but that doesn't really describe it for you guys. So I'm gonna go up here to straight slot. There are options. You can do center point straight slot, 3-point arc, center point arc. We just need to do a straight slot. So we're gonna pick these 2 points at which the slot ends, I guess, and then we sort of drag out. And then I'm gonna say, yeah, we can make that to be equal. So it'll be perfectly flush with our Falcon 500s. Maybe I skipped over something. I can't really think of anything, but that's really all a slot is. You define the 2 points that you want it to start and end, and then you define how fat you want it to be, and you can do that by taking one of the circles, one of the half circles in the slot, and relating it to a circle that you already have, which we already have our 2 circles here. So that's all that is. And then all we do is we go and extrude this 0.25. It'll be a 1/4-inch plate. Cool, isn't that cool? That's so cool. We got a plate. Awesome. So I'm gonna save this. We're gonna call this transmission motor plate. Cool. Cool. All right, and then I'm just gonna make a hex shaft because I don't want to have to look at Vex Pro for a hex shaft. So to make a hex shaft, you literally just put a hexagon down. If you really want to be fancy, you make this vertical, and then you define this to be 0.5 inches. I don't know why I don't. My SolidWorks always defaults to metric system, but I don't know why. I need to fix it. But we're gonna just extrude this. We're gonna call it 5 inches. Cool. And there we go. That's our hex shaft. So I'm gonna save this. Hex shaft. Cool. We will go into naming conventions and how we do all that later. I don't want to go into that right now because I'll go off on a stupid tangent. But anyway, now we need to go to each of our things that we need, and we need to download them. So I'm going over to the Falcon 500 thing. I'm going to go over to CAD files, download it, go over to bearings. I need a 1/2-inch hex bore. Bore means the center thing. So like that's a hex bore right there because it makes a hexagon. That's a round bore because it's a circle. And then if there were one that had like the weird falcon spline thing, like that right there, that would be a spline bore or a falcon spline bore or whatever you want to call it. So then we can, so I'm gonna need a flanged bearing as opposed to a radial bearing. I need it to be hex. I need it to be 1/2 inch hex. Perfect, right here. So then I go and I just download that. And then 20 dp motor pinions, I need to go to CAD files. I'm looking for a 12-tooth Falcon. So Falcon 500, 12-tooth steel gear, that works for me. And then our 1/2 inch gears here, and then we scroll down and we go over to 48-tooth gear. It doesn't matter that it's aluminum, that doesn't really matter. And then we download it. Okay, so then once you download all those things, you're going to make a new assembly from this transmission motor plate. Probably should have done that a little bit slower, but you're going to go up there and you're going to make a new assembly from the part, and then we're going to be inserting these things in. So we already have it selected by default, then we just click it in, and then I need to insert. I'm just gonna put in the hex shaft, and then insert, browse, all files in F49, and then I can just open all this. Oh crap! I need to do it one at a time. So these are the flanged bearings, and I could go in and I could go to browse and click it and find the file each time, but I could also just click this push pin and just put it in twice and then check mark once I'm done, then insert another component, do the same, all files, Falcon gear, push pin, put it in, check mark, insert, browse, all files, Falcon 500, these motors and electrical components are very heavy. They have a lot of stuff in them. It's just a bunch of wires and crap that we don't even use. But we'll just leave it in because, I don't know, it just take time to delete it all. And I actually tried deleting it and it didn't work. I had to suppress the different things and it was all confusing. But these are going to take a while to load in. All right, so it's loaded in, and then let me see if I can, yeah, there we go. I can push pin it and then put one in, put the other in, and then check mark, I'm done. Then insert, all files. I need my, what do you mean? Oh, that's weird. It's just a file? What the heck? Let me reload this. Ah, yes, I love it when it spasses out. Oh, nope, that's just a file. Okay, that doesn't make any sense. But okay, I guess we're gonna go to West Coast products 20 dp gears. No, literally just any gears. Aluminum hex bore gears. There we go. Is this the right one? So if you don't know, West Coast Products is a different distributor, but it's basically Vex Pro. In fact, all the things that Vex Pro has, West Coast Products has, because they just get things from Vex Pro. So here we go. We can get this download, and then finally we get that right there. And so then I can. Oh, I'm gonna have to cut this again. Then we can put this in. And there we go. Actually, I really hope that's a 1/2 inch. Is that a 1/2 inch hex? Oh my gosh, it's a 0.375 hex. One sec, I'll be right back. I'm just gonna cut and get the right one, and I'll put it in. Okay. Okay, I finally got it now, so can insert it, go to all files, and import the right one, and there we go. So now we finally got it. So now I've got a bunch of random pieces, and I need to connect them all. But I'm actually missing one last piece. So I'm going to go over to my transmission motor plate, and I'm going to save as. I'm going to save as a copy and open. This means I'm going to, one sec, our plate. This means I'm going to duplicate this and then open the duplicate. And so now we have a copy of it, and then I can make changes to this without making changes to the other one. So I'm going to, we can keep the original document. So now I'm going to edit this sketch, and I'm going to, I know this wasn't detailed in my sketches, so if you didn't do this, it's like not even a big deal. But I'm just going to go and change all these holes to be for construction, and then I'm going to make my own hole pattern. And this is going to be 1.75. And this is going to be 3.5. And then we're going to call that for construction. I'm actually going to make that 1.5. Yeah, that'll be better. And then I'm just going to make my holes. So those are equal. Those are equal. Those are equal, and those are equal. Okay, so if you don't know what I just did, I basically changed the hole pattern to be this. It looks weird, but basically we'll have a 2-inch beam that goes along this, and then we'll just mount it to that. That's the idea. We won't literally do that, but the idea is that we'll just have it mounted to the 2x1 beam or something. Yeah. So we're basically just changing the hole pattern because we don't need to mount the falcons on either side. So then we're going to go back to the assembly, and then we're going to insert our final thing, our transmission bar plate. Going to put it right there. And then we're going to, oh, actually I might have made a mistake. Yes, I did. I made a mistake. Because what we do need to do, let's see if I can find it. Yeah, transmission bar plate. SolidWorks is auto-saving, so it's going to take a while. Oh, between my plates, I need to put standoffs, which I actually did not put in my list of materials that you'd need. So that's a mistake on my part as well. But we're going to go, and I'm just going to have, yeah, we'll put them, no, that's not good. Let's put them, here, I'll change up the hole pattern. I'll make this 3 inches. Yeah, that's better. And then I'll make this, I'll make these the places where we put standoffs. So those holes exist now. It looks a little weird, but it's all good. Yeah, that's where everything goes. And then, okay, cool. Yes, rebuild the assembly. All right, so now we can actually do the bit where we put everything together. So first I'm going to relate my 2 plates to one another. I want them to be concentric. You have to define 2 places where they're concentric for them to be fully defined in that plane. And then how far apart did I have them in that sketch? I had them let's have them at 0.8. So we'll take this, this, and we'll take this, and we will set them to be a distance. And we're gonna, oh my god, freaking metric. We're gonna call it 0.8 inches. And we gotta check that. Then I'm gonna reset my default to be and inches, and then I'm going to mate my bearings to the holes that they go in. So that's concentric to that. Oops, I need to undo that because I need the flange to be on the right side. So right now the flange is on the wrong side, so I flip that, and now it's correct. And then I take the flange, and I make it coincident to the plate. And then I repeat the same thing for the other bearing. I do that, and then I move it a bit, and I take the bottom, I make it coincident, and then, okay, cool. And then I'm gonna take, the Falcon gears are annoying to try to mate to the thing, so what I do, at least it's worked for other things, I can take that and I can take that. Cool, yep. So these right here are, I guess, on a curve, so you can make it concentric to the hole. And then I'm gonna make this, I'm just gonna make it coincident because that makes it easier for me. Because I guess the right thing to do would be to make it point, oh, what would it be? 0.025 or something. I don't know. Yeah, I think 0.025 is the right thing. Distance from either edge of the thing to make it completely within the middle, but I honestly don't care. And then make this, and then you need to make these be parallel so that whenever I rotate this, oh, that's spazzing out, but whenever I rotate it, it stays, you know, within the same thing. And then this is coinciding to that. Okay, cool. And so now we've got all the gears together, and then, okay, hex shaft. This is really annoying. And there's actually a thing that you have to do, and I don't know how much I want to do it, and I first need to check if I can do it. So before I mate the hex shaft, I'm just gonna mate these falcons to their respective holes. And then important thing with falcons, if you do it one way with one falcon, you want to make sure you copy it to where like these tags are like parallel with each other. So I have to make it to where I think it's this guy right here is gonna have to be concentric with that guy right there, and that concentric with that. Okay, and double check, make sure I did it all right, and yep, there we go. Cool. So that's what we want to do for that. And then hex shaft. This is annoying. Again, I didn't detail this in, like, I didn't talk about this whenever I talked about the things that you would need, which again is my fault. But after you would make this, I'd be like, oh, well, you missed this and you missed this. Then you'd go back and you'd put this in anyway. I actually didn't fully define my falcons, so I need to do that. And while SolidWorks autosaves, because I need to make this coincident with the plate. All right, so now that that's there, and then we can take I think that's it. Okay, so now we get to the hex shaft. So first, let me make this bearing match that. Cool. So now that's that. So if you're doing straight lines, faces, you need to make 3 faces together to get it to be fully defined. So 1, 2, 3. Okay, cool. So 3, and then this shaft is not going to be going anywhere. And so that can rotate, and the gear is going to rotate with it. Now here comes the tricky, annoying bit. If I take this and I just rotate a little bit, we can see that it clears the falcons. But if we were to be actually making this, we would need to make sure that nothing moves around. So there's 2 ways that we would do this in real life. We would either use Eclipse, which is the better option, or we would use a tapped hole and a bolt and a washer, which works just as well, but we can't actually do that with this because there's not enough room for a washer here. So what we're gonna have to do is we're gonna have to put in Eclipse. And if you don't know what Eclipse are, it's basically like a little insert you put into the shaft to stop it from moving. So we're gonna have to go back to VexPro. So VexPro Eclipse. I don't know if they actually have Eclipse. It might be just McMaster-Carr. Eclipse. No, they do not. So we go to McMaster-Carr. This is probably the best website in the world. Not even joking. Just, it's so nice. It can be a lot at first. But once you get this sort of general idea of what everything is, this is literally the most wonderful website in the entire world. So we're going to need to find retaining rings. We call them Eclipse, but they're actually retaining rings. So maybe they call it Eclipse. Okay, yeah. So Eclipse side mount retaining ring. So we need the outer diameter. Sorry if this is getting really, really complicated, but this is sort of what you're gonna have to do. Not that everything is gonna be Eclipse and whatnot, but this is probably gonna be really similar to the things that you're gonna be doing. So I'm gonna say, hey, put some Eclipse in there, and you're gonna be like, okay, how the heck do I do that? So you need the outer diameter to be bigger than the shaft that it's on. So our shaft is 1/2 inch. So our outer diameter needs to be bigger than 1/2 inch. That's going to be easy peasy. Then we need the inner diameter to not be insane. So so right here we can see for outer diameter. So this is going to be for a 1/2 inch. Is it 1/2 inch on all? Yeah, we're going to say it's for a 1/2 inch shaft. Yeah, we're going to say it's for a 1/2 inch shaft. And so The outer diameter is 0.8, and then the groove. This is what matters for your CADing. The groove is 0.396 in diameter, and then 0.046 in width. So whenever we go to our hex shaft, we're going to need to be cutting that to those specifications, but we also need to find out where the heck we're going to be putting these. So I want to put an E-clip I want my shaft to be flush right here, and then I don't care where this gear goes. But I'm gonna say an E-clip right after this gear, and then an E-clip right on the other side of this plate. So once SolidWorks stops loading, I could actually figure that out. Okay, so we can find the distance between the shaft, and it's about 1.3. Okay, and then the distance from here to here is about 0.5, a little less than 0.5. So I need to have so what were our specifications again? It was, what was our radius? It was 0.396. So we go over to our hex shaft, and we say that is 0.396 inches. All right, then we check that off. I need to put that to, yeah, okay. And then we edit the sketch. Then we go over and we extrude cut. Okay. And I need the groove to be how big? 0.046. So we go over here and we need it to be 0.046 inches. All right. But then what I need to do is I need to do offset from this surface. Is it going to let me do that? Oh, wait. I know what to do. Go back to extruded cut. We need to offset the sketch plane. So we do it from an offset. So that offset is, so this is 0.046. And then the offset, we had it, wait, what was it? It was 1/2 inch. So, so 0.5 minus 0.05. And we need to flip that. Because we were measuring from where the gear started. So right here at the second yellow line, that's where the gear starts. So we need to put it back. And then if we do that, whoopsies, I did the wrong thing. So I need to edit feature. Okay, yeah, so this is right and everything, but I just need to change my sketch. So my sketch needs to instead be, well, actually, I don't even need to change the sketch. I can edit this, exit the sketch. Actually, let's see if this will work. Can I do flip side to cut? Let's see if that works. Yes, okay, cool. So now I've got my groove. So if you don't know, flip side to cut, instead of cutting the hole that I made, it cuts the negative space. So it just flips what it's doing. I don't know if that made any sense whatsoever. But okay, that made me feel very, very cool. Very cool. So I already forget what this is over here. This distance, I think it was, yeah, 1.3. And then we go to our hex shaft. Shaft, hex shaft, loading, loading, loading. And then I do the same thing. I think 0.396, yeah, 0.396. .396, and then I check that, and then I'm gonna do extruded cut. I need to flip the cut. I need to do it from an offset, and I need the offset to be 1.3, and I don't need to subtract it this time because that's where the bearing starts. So hopefully I did this right, and then we'll see this all work out. I need to make that coincident. Ah, crap. And I screwed everything up. All right, so whenever you need to go back and undo something like this, hold on, let me collapse everything. I'm gonna go up and I'm gonna collapse all the items. I need to go to the hex shaft, all the mates, and I need to delete all of them. So it's gonna take a while to load. It's gonna take a long while to load. All right, so now I take all the mates and I delete them, yes to all, and then I do it all over again, but this time, since I have a circle, since I have a circle, I can make it concentric. And then I can flip it around. There we go. Cool. And then I can make that, mate with that, and then, yes, perfect. I have a nice little groove right where I wanted it. And then I have a nice little groove right there, right where I wanted that. I'm actually going to move this a little bit. First, let me define this to be with that, parallel with that. And then I'm going to just evaluate this to see where I went, just to see the little discrepancy. So there is a, oh my God, 0.0065. So I need to go back 0.0065 from that. I think it was the first one I did. Yep. So minus 0.0065. And then let's see how that looks now. And then, perfect. It's nice and flush. Almost. It's good enough. It's good enough, honestly. Yeah, so that's everything now. We have our Eclipse slots in. Now we just need to go and download our Eclipse. So McMaster, it's a little different from Vex Pro in that you find exactly what you need using the sidebar here. And then you click on the number that you need. Is this what I want? Yes, this is what I want. You go to the thing that you need, and then you're like, yes, I need that. So you go over to click on the number, you go to this little thing where it says product detail, and then it says CAD. And then it takes you to this page. And then This is if you're buying it. This is if you're CADing. So you're going to go and you're going to save. And I have it, if I think the first time you do it, you have to like do all these things like, yes, I'm using this software. We're using SolidWorks. And then I can go into the assembly and I can insert my 2 E-clips. And then I'm going to push pin that so I can insert both of them. Then I can check that. And then, yep, we can see that our E-clips are right there. Then once SolidWorks finishes loading, like it does every 30 seconds, then I can take this and I can make it concentric, make it concentric. I actually need to hide that. And then we can mate them to the sides. Then we can do some additional things just to fully define it, like I want these to be parallel. I want this to be parallel with the other E-clip. And that way it just stays fully defined. And then I can go back and I can show this. If you don't know what I just did, you can go in and change whether or not certain items are invisible, and that will make it easier for you once you're, like if you're trying to find something that's hidden inside an object, then you can just hide it and then bring it back in and have everything work. So now, this is where we're at. We have this shaft and it rotates and it's locked in with these 2 E-clips right here and right here. If you don't know why I chose these 2 spots, it's just to retain it completely. Like it can't move that way and it can't move the other way. So it's all locked in. If you somehow did all of these things with the 2 different types of plates, with the E-clip mounting, with everything, holy crap, dude, kudos to you, because I didn't even remember all those things whenever I was putting the sketches together. If you didn't, no sweat. Like, it's not a big deal at all. We actually didn't even put in the standoffs. I'm not actually going to bother with that. So what you would do for the cadathon is you would make everything fully, you don't leave anything up to the imagination. If there are supposed to be standoffs there, you put them there. So you would make like some hex standoffs and you'd put them in and you'd have to countersink this side of the hole, so then you could put the screw in and you'd do all these different things. Then you just put it all in. You don't leave anything to the imagination. You also put in the mounting bolts for all the Falcons. You do all those things. Is there anything I'm missing? Other than the standoffs and the bolts, I think that is it. So congratulations, you made your first assembly. If you didn't get to this or something very, very, very similar to it, then I will have you, well, I would, during F4, I would say, hey, you didn't put in E-clips. And I wouldn't tell you how to put in E-clips. hopefully you would just be able to do it yourself. Or I would say, hey, you didn't put in standoffs. And then you would go back and you'd put in standoffs and you'd show it to me again. I'd be like, you didn't put in the bolts. And then you'd put in the bolts and you'd show it to me back. And I'd be like, well, that's great. You've got everything you've got there. Good job. And then I'd hand you your next assignment and then you do it all again. So I think that's the rough structure we're going to go about these, that I'm going to go about with this whole competition. We're going to see how it works. If it works, it works. If it doesn't, well, all right. We have another cadathon in the winter, and we'll do that then. But for now, pat yourselves on the back. You got through this whole thing. Took way longer than I thought it would, and that's pretty much the story for all the CAD ever in the world. So yeah. So thank you guys for agreeing to do this, and I guess good job on your different CAD things. If you want, I don't know how I'm going to send this to you. I might do it through GradCAD, and if so, I would love for you guys to put in your own assemblies. If I'm not doing it through GradCAD, I wouldn't know how else you would do it, so I'll just send it to you through GradCAD. Yeah, so send me your assemblies, upload them, like call them Dan McDonald, like do it all in one folder and call the folder Dan McDonald assembly, transmission assembly. But obviously instead of Dan McDonald, you'd put like Sai Samasetti or Sovereign Chinkraner. So yeah, send me your things. I'll give you guys feedback. Don't be worried about not having things because I didn't even have everything. So yeah, good job. And that is it for this.